Hi everyone, welcome to this session where we are going to discuss a joint physics form 2 paper that was done third term in 2023. The reason as to why I'm opting for this discussion, I went through the paper and I saw the paper being so involving and very important to learners, so those preparing for exams and also those who want to advance their skills. Straight to the point, we are going to question number one. Keep inviting your friends, share the link to friends so that they may also benefit. With question number one, they say, the micrometer gauge below has an error of negative 0.19 millimeters. Determine the total thickness of the object. So maybe first of all, let's get the reading on the thimble scale and the sleeve scale. Let's get the readings. When you look at this reading here, this is 0, 1, 2, 3. Then below it, you can see easily, below it we are having another dot. So this is 0, 0.51, 1.52, 2.53, then 3.5. So you can see that as 3.5, 3.50, then plus this is a 0, 1, so that is 0.01 plus 0.01. So you're going to get that's 1, that is 5 point here, that is 3.51 millimeters. 3.51 millimeters. Learners, remember at the top we are having a negative 0 error. How do we correct a negative 0 error? We normally correct a negative 0 error by addition. So that will now be 3.51. We are going to add 0.19. When you do the addition, this is 0, carry 1, this is 7, then this is 3, that is 3.70 millimeters. 3.70 millimeters. 3.70 millimeters, and that is exactly what was required of us in that question. Let us see question number 2. Two mirrored walls stand at an angle to each other. A student in a room counts 9 images of himself in the mirrors. Determine the angle between the walls. How do you get the number of images? Learners, we have the formula. Number of images, which is n, is given by 360 over theta, where theta is the angle in between the mirrors. Then you subtract 1. So having said that, it is now 360. So n is the number of images. We are now having 9 images, so 9 is equals to 360 over theta minus 1. Collection of like terms, so that will now be 9 plus 1 should be equals to 360 over theta. So that is 10 is equals to 360 divided by theta. I want to remove this. I want to remove my theta. I multiply here by theta, also this side by theta. I'm now going to get, when I do that multiplication, 10 theta is equals to, in this case the theta and the theta will cancel, so I'm going to get 10 theta is equals to 360. Once I get like that, in order to remember, I'm having that 10 theta is equals to 360. I want to remain with theta. I divide here by 10. I also divide here by 10. So learners, I'm going to get my theta as 36 degrees. 36 degrees, and that now will be the angle between the two walls. The angle between the two walls. The angle between the two walls. Keep inviting your friends, learners. It's a very important paper. Be it you're in Form 2, you're in Form 3, you're in Form 4, you're even in advanced levels, you just want to enjoy doing physics. This is a session for you. This is a session for you. Question number 3. What is meant by the term anomalous expansion of water? Anomalous expansion of water. So we normally say anomalous expansion of water is the unusual behavior of water in which it contracts when heated from 0 degrees to 4 degrees, then starts now to expand as any other liquid. Learners, what we know, any object upon being subjected to heating, we expect it to expand, and upon being subjected to cooling, we expect the object to contract. But water behaves in a weird manner, or in a unique or different manner, such that when we heat the temperature of water from 0 degrees to 4 degrees, this water tends to contract instead of expanding. So that unusual behavior of water contracting as the temperature rises from 0 to 4 degrees is what learners we call as the anomalous expansion of water. It's not normal. Anything on heating has to expand, but water proves us different. So that different behavior of it is what is called anomalous expansion of water. So in our definition we can say, is the unusual behavior. We can say is the unusual, is the unusual behavior of water. The unusual behavior of water in which it contracts when heated as its temperature rises. As the temperature rises from 0 degrees Celsius to 4 degrees Celsius, then starts to expand, as any other liquid, as any other, starts to expand as any other liquid, That weird behavior is what is called, because we expect it as long as the temperature is rising, we expect the water to expand. By the fact that it is now contracting, that's unusual behavior, and that's what we call anomalous expansion of water. Explain any two applications of contraction and expansion in solids. Any two. We can have even railway lines. When you look at your railway lines, they are being left with some gaps. That's an application. So you can say the railway lines are constructed in sections with expansion gaps, and the sections held together by fish plates. The bolt holes in the rails are oval to allow free expansion and contraction for rails as the balls move freely in the holes. So we can say one application is explain two railway lines. Railway lines have gaps. Railway lines have gaps to allow for expansion. Another thing that we can talk of it is the pipes carrying steam. You will find them are fitted with loops. Pipes carrying steam are fitted with loops. Pipes carrying steam are fitted with loops to allow for expansion. When steam passes through them. You know, steam is very hot. Steam passes. When steam passes through them. Any other application? They just wanted any two. There are so many literally, but those are some of the few. A body weighs 600 newtons on the surface of the Earth and 450 newtons on the surface of another planet. Calculate the value G in that planet. This is a question on mass and weight, so it's very important for us to be able to state the relationship between mass and weight, whereby the relationship is that weight is equals to mass times gravity. Remember, mass is constant everywhere. So if this body has a weight of 600 newtons on Earth, so that's like saying 600 newtons is equals to the mass, which we don't know, times the gravitational force on Earth, which is 10 newtons per kilogram. So when you do that division, 600 newtons divided by 10 newtons per kilogram to give you your mass, you'll realize the newton and the newton will cancel out. So you're going to get also, as the newton and the newton cancels out, the 0 and the 0 here will cancel out. So you're going to get your mass. The mass of that object is now 60 kg. If you've gotten the mass as now 60 kg, dear learner, remember that mass is always constant everywhere. The mass you have on Earth is the same mass wherever you go. but weight may change due to changes in the force of gravity. Now they say this same the same body weighs 450 newtons on another planet. Because this is a weight, remember its mass will just remain the same. There is a change in the force of gravity. How do you work it out? So weight, which is 450, should be equal to the mass, which I've now gotten as 60, times the gravity, which you are looking for. If I want to compute it, now I know that gravity is equal to 450 divided by 60. The force of gravity in that case is given by 450 divided by 60, and that should be 7.5 newtons per kilogram. 7.5 newtons per kilogram. 7.5 newtons per kilogram. Question number 5, sorry. State the applications of electrostatic charges. State the applications of electrostatic charges. One application we have is the electrostatics precipitators. We have the electrostatics precipitators. Electrostatics precipitators. Another application of the charges is what we do implement in fingerprinting. Fingerprinting. We may also have even spray painting. As another application. Another application, even in photocopying that we do on daily basis. Photocopying is an application of electrostatic charges. Those are just among the few. Question number 6. 200 coulombs of charges passes through a point in a circuit for 0.6 minutes. What is the magnitude of current? This is from cells and simple circuits. I have the general formula with me. Q is equals to IT. They want what is the magnitude of the current. Remember, when they talk about current, we normally define current as the flow of charge, the amount of charge, which is Q, flowing per unit time. So now learners, in physics, make sure any calculation you do, you are doing with units in their SI. Make sure the units are in the SI units. Charge is being measured in coulombs, so it's 200 over the time, which is 0.6. But now, remember, time being a measure of duration of an event, SI unit should be in seconds, and this one is in minutes. So any calculation in physics, you must ensure it is in SI unit. So the SI unit of time is seconds, so you multiply that by 60 to bring it to seconds. When you do that, you are going to get that is 200. Divide that by 36. And when you have 200 divided by 36, you are going to get 5.556. Because it is current, the SI unit is ampere. Any calculation in physics, make sure you're dealing with it in SI unit. It's SI unit. Question number 7. While heating water in a beaker, a wire gauge is placed below the beaker. Explain the role of a wire gauge. While heating water in a beaker, a wire gauge is placed below the beaker. Explain the role of that wire gauge. We normally use a wire gauge because it's a good conductor of heat. It therefore spreads the heat to a large surface area of the vessel. Without the gauge, heat will only concentrate at one point, which may lead to uneven expansion of the glass, hence breaking. So why do we use this wire gauge? Remember, learners, a wire gauge is a good conductor of heat. It will absorb the heat from the source of heat, then try to spread it to a larger surface area. Once it gets spread to a larger surface area, the glass will gain the heat uniformly, all the surfaces, therefore preventing it from breaking. So we can reframe our statement and say, when heating, a wire gauge is placed below the beaker. Explain. So you say, wire gauge is a good conductor of heat, comma, it therefore spreads the heat, spreads the heat to a larger area of the vessel without the gauge. Without the wire gauge, what would have happened? Let's see. Without the wire gauge, heat will concentrate at one point. Which may lead to uneven expansion of glass. Uneven expansion of glass, hence it will break. Let me say it may break. Yes, so that's how you need to reason that the wire gauge is a good conductor of heat. It will therefore conduct the heat and spread the heat to a larger area of the vessel. Without the gauge, heat will only concentrate at one point that is being hit, that's receiving heat at that point. The other points may not receive heat or may receive the heat late. Due to now that like uneven expansion, the glass may break down. What is the relationship between physics and technology? Learners, I want to stress on this. Don't ignore these simple questions. If you've gone through the KCSE questions, even in 2023 KCSE, they were asked the relationship between physics and physics and history. So never ignore anything in physics. Examiners are becoming quite tricky. So let's answer the question. What is the relationship between physics and technology? How do they relate? You see that As technology is advancing, the machines used in the field of medicine, such as we've got the X-rays, the body scanners, the lasers, are all applications of physics, and that the machines came as a result of technology. Long time ago, before technology came in, those machines were not there. So it is the advancement in technology that has resulted into advancement in the field of medicine. For example, we've got nowadays X-rays due to technologies, but all those machines apply the knowledge of physics. So that's a relation. We can also think of it like this. The physics knowledge is also used in defense industry in the manufacture and use of modern and complex machines. Yes, technology is advancing such that we are now coming up with machines that can really help us fight our enemies. But remember, as we are calling it technology, we are applying the physics knowledge in coming up with these machines. Also, we can say the manufacture and the use of satellites and microwave dishes used in information technology to relay information is based on physics knowledge. So let's start our how will we say this, the relationship. We can even just say the machines used in the field of medicine, machines used in the field, let me just say in the field. Okay, let's just proceed. In the field of medicine, the machines we use in the fields of medicine, e.g. X-rays. That one is very common. Someone has a fractured bone, is taken for an X-ray. Machines used in the field of medicine, e.g. X-rays and lasers. Obviously, there are so many, I cannot list all of them. Are all applications of physics. Are all applications of physics. How true is this? We are using X-rays in hospitals, but also in Form 4 we have a topic by the name X-rays. So we are studying it in physics and taking the physics knowledge and go building those machines. Then we can also say if the physics knowledge is used in defense industry. Another relationship, physics knowledge is used in defense industry. In the manufacture and use. In manufacture and use. In the manufacture and use of most modern most modern and complex machineries and complex machines. Learners, even those AK-47s that you do here, they are using the physics knowledge in building them. They're using the physics knowledge. We can also talk about they want any relationship you can give. Maybe I can just give you the last one because this is just a revision. You can even talk of it as the manufacture and use of satellites. Manufacture and use of satellite. Manufacture and use of satellite and microwave dishes. and microwave dishes used in IT, to relay information, learners. To relay is to pass. To relay information, is based on physics knowledge, on physics knowledge. So any relationship you may find it easy on your side. I know there are some others that have left, but it depends. Just give it well. Relate, how does it relate with physics? Technology, link it with physics, and vice versa. Question number 9. Hope you are following. Using the domain theory, distinguish between magnetic material and a magnet. Using the domain theory, distinguish between magnetic material and a magnet. How do we distinguish this? Remember, the difference should come out using what? Using the domain theory. And hope learners will all recall what domain theory is. Now, what you will learn is that, for a magnet, the dipoles in all domains align towards a common direction after it has been magnetized, right? While in a magnetic material, the dipoles in different domains are aligned in different directions. So that is the main difference. That is the main difference in terms of domain theory. So you can say, for a magnet, you can say, for a magnet, the dipoles in all domains, the dipoles in all domains align towards a common direction. While in a magnetic material, dipoles in every domain, dipoles in every domain are aligned. The dipoles in every domain are aligned in different directions. Now, how will you distinguish this? A magnet is already having magnetism in it. So, because it has already magnetism in it, when a magnet is having magnetism in it, all the dipoles in all the domains face towards one direction. That's a clear indicator that even if it was a magnetic material, if all the domains have aligned in one direction, then that magnetic material is a magnet at that time. But for a magnetic material, it may be a magnetic material, but it does not have magnetism at that time. For example, one of the magnetic material is a nail. A nail will have the dipoles in different domains facing different direction. I may have a magnet by the name, maybe a bar magnet or a U-shaped magnet or a horse magnet, whichever you know. All the dipoles in all the domains will be aligned in one direction. So that is a very, very major difference between magnet and magnetic materials using the domain theory. State two applications of convection in liquids, in fluids. Any applications of convection? We have the land and the sea breathing, right? That is one application, land and the sea breathing. Land and sea, the land and the sea breeze. That's an application of convection. Another application is the cooling system of the car engine. I hope you can explain these explanations, learners. Cooling system of car engines. The cooling systems of the car engines. Another application I might give is maybe the domestic hot water system. Domestic hot water the domestic hot water system. We can have also the ventilation. And many more, learners. Ventilation. So those are just some of the few applications you should be able to explain. Convert a temperature of 234 kelvins to degrees Celsius. Remember, learners, what do we do here? When you are converting Kelvin to degrees Celsius, do you add 273 or you subtract? You subtract, right? So with this one here, the temperature will be given by 234 minus the 273. What do you get there, learners? You're going to get negative 39 degrees Celsius. Negative 39. So Kelvin to degrees you subtract, degrees to Kelvin you could have added. When you have that as your point of reasoning, then it will make your work quite easier. Section B. State Hooke's law. Remember that laws and principles in physics are stated the way they are. Don't come with your own language and put it there. So for us to state Hooke's law, we say for a helical spring or any other elastic material, for a helical spring or any other elastic material, any other elastic material, extension is directly proportional to the stretching force or rather to the applied force, to the stretching force, provided that the elastic limit is not exceeded. Provided elastic limit is not exceeded. exceeded. So when we are looking at your law, there are things that we need to see. One, tell us extension is directly proportional to the stretching force. Also tell us that this elastic limit should not be exceeded. Then the material used should be always a helical spring or any other elastic material. So you see, each and every term there seems to be important. Now because you are talking about extension, I've stated my law. I'm just giving some elaborations. Maybe let me put them here. Because I'm talking about extension is directly proportional to the force applied. So this can be K E is equals to F. If I introduce a constant there, direct proportionality. Let's see. In an experiment to verify Hooke's law, in an experiment to verify Hooke's law, a piece of rubber was fixed to a rigid support and the other end pulled with a force of ranging magnitude. The values of force and extension were recorded as in the table below. We have a row for force. We have another one. The force is in newtons, then the extension is in centimeters. Plot a graph of force against extension. Even you've been helped. You've been told that force should be on the y-axis against extension on the x-axis. Now learners, in most cases you'll find you've not been told like that. But always, if you are told plot a graph of this against this, whatever variable they've begun with, that should appear on your y-axis. Then what follows after the word against should go to your x-axis. In short, plot y against x, not x against y. Should be y against x. Now remember that this is a question also that can easily come in a practical. So learners, I want you to be so much attentive in this section so that you understand what is required of you. We need to do the plotting. With the plotting, first we need to identify the most suitable scale. Let's look at our graph. Because force should appear on your y-axis, look at your values for force. We have 0 to the lowest value is 0, the maximum value is 1.4. Extension, the lowest value is 0, the maximum value is 7. So because those values are so small, the values on the force, how will you plot 0 to 1.4? Those values are so small. We are going to multiply those values by 100. Okay, let me multiply them by, should I multiply them by 10 or 100? Because let me multiply them by 10. Let's multiply them by 10, such that when you multiply them by 10, the lowest value will be 0, the highest value will be 14. At least you can now do that plotting. You can now do the plotting. So let's proceed. Let's proceed with it. Let's proceed with it. Let's proceed with it. 1, 2, 3. I'll use my ruler. I use my ruler to have it quite plotted. I want to draw my y-axis. I'll come here. I want to draw. Let me use a red ink to make it distinguishable. I'm done with that. Maybe let me rub it. I don't want to stretch it so much. Let me have it up to here. That is my y-axis. Let me also draw my x-axis. Just a moment, I'm drawing my x-axis. I'm drawing my x-axis like that. After you've drawn your axis in physics, you label your axis. So the x-axis will have extension. I'll have extension here. I'll have extension. You label axis with the correct units. That's how we do the marking. What's the unit for extension? Centimeters. So it's extension, then inside it is centimeters. Then your y-axis should be force in newtons. Force in newtons. So how will we have that? That will be force. The unit is in newtons. We'll see what we'll do later. But so far I've labeled, or axis labeled with units. Now because I've said we are going to multiply the force with 10, so that will be 0. I want to go with the intervals of because the maximum value here will be 14, I can go with the intervals of 1. Obviously this is the origin 0 0, 1 2 3 4 5 6 7 8 9 10 11 12. It will be less. Sorry for that. I thought my graph will be enough, but seems it does not fit. If it does not fit, what will I do? I want 2 5 7 1. Just a moment, let me make sure. Let me make sure that it's fitting. It's fitting. So that means I have to stretch this line. Let me stretch it fully so that it's correct. Then I now have to do it like this. I'm sorry for that, but it's not that it's an error. It's just that sometimes it happens. That's why we advise you to do your drawings in pencils. So this one, we had labeled this as extension, and its unit was in centimeters. So this is 0 1 2 3 4 5 6 7 8 8 9 8 9 10 11 12 13 14. 1 2 3 4 5 6 7 8 9 10 11 12 13 14. On my x-axis, so you realize, because this is 14, what happened? These values, I multiplied them by 10 to make them like that, but the original values, if I have 14 here, I have to multiply this 14 by 10 power negative 1 to take it back to, in fact should be by, yes, by 10 negative 1 to take it back to where it was, 10 negative 1. So these ones here, I'm going to multiply them by 10 negative 1. So this was times 10 negative 1, such that if I'm having 1.00, that 1.00 is here, that 1.00 is the 10. If I multiply 10 times 10 power negative 1, it will become 1, which is the same as 1.00. So we need to be that observant. We need to be that observant. What if Yes, we need to be that observant. Our y-axis, sorry, our x-axis 0 to 7, so that one you can just go directly. Let's see, 1 2 3 4 5 6 7. Yeah, this one even I can go with this as the intervals to utilize enough space. 1 2 3, sorry, let me write well, 3 4 5 6 7, like that. That one there's no multiplication, it's just direct. So we see 0 0. What is the point 0 0? You do your plotting. Let me do it with a green pen. Then e 0.2, this becomes 2, then 1.5, 1.5 2, 1.5 is here, then 2 on your y-axis, 1.52, then 2.5 5.5, 2.5 5.5, 2.5 5.5, 5.5 is between 5 and 6, 2.5 here, 1 2, that is 2.5 5.5, then 3.5 7.5, 3.57, 1 2 2.5, somewhere between, sorry, this is not 7.5, I've plotted on 6.5, Apollo should be on 7.5, 3.5, 7.5 is between 7 and 8, between 7 and 8, 7, yeah, there. Then I'm done with 3.5. I'm now going to 4.51. 1 is like 10 because you're multiplying them by another 10. So 4.5 10. 4.5 is here. Where is my 10? My 10 is here. Then after that, 6 13. 6 13. 6 is here. You go up to 13 on the y-axis. Then finally 7 14. 7 14 at the edge here. At the edge there. Learners, because it is like that, it's a practical that was done. Don't expect all the points to be on a straight line, but when you draw your line, make sure it's passing through more, at least 3 points, at least 3 points. You know that a graph of force against extension should be a straight line passing via the origin. So with the help of a ruler, let's have it positioned. Let's have it positioned. Let's see how will it pass through the most of the points. If I say like this, I'll have only passed through 1 point. If I make like that, another one. If I make it like, my ruler is not that, it's not that simple to position, but let me see. I think that one can be better. I think that one can be better. Let me see. I think that one can be better. Wonderful. I think now this one is well positioned. Let me draw using this one. Like that. Then you can see from here, because it is not there, you don't leave out that point. It's a straight line. Then here seems like the elastic limit was exceeded, and because the elastic limit was exceeded, now you realize extension was no longer directly proportional to the force applied. Very nice. So I've drawn my graph. You can see. They want we let me enlarge it to make it visible now, because I'm done with what I was saying. After we've done that, you now have all your marks, because you've labeled your axes with units. You've used a simple uniform scale. Yeah. From the graph, determine the spring constant. From the graph, determine the spring constant. How do we determine the spring constant here? The spring constant, let's first see our gradient. I can see it passing via this point. Let me see. Let me use a different ink for that. This is my ruler. I want to maintain accuracy here. You just pick any of your points, then you make sure you are showing. I'm picking any 2 points. The way I've picked. What's the coordinates here? The coordinates here are 2, 4. The coordinates for this point here, remember, are 2, 4. The coordinates for here are 0.51. Let me use a different ink on that side. 0.5, 1. That's very nice. Let's get a slope. Slope, in math we call it gradient, in physics we talk of it as slope, is change in y, which is change in force, over change in x, which is change in extension. And with this formula that I wrote here, F is equals to KE. Let me just see. If I have F is equals to KE, then K is equals to F over E. Remember, K is your spring constant, so it means F over E, the one we are calculating here, will give us the spring constant. Then we proceed. Let's look at the change in force. Pick the value here. Force was on our y-axis, so 2 minus 1, not 2, 4 minus 1, 4 minus 1. But remember, our force was multiplied by 10 negative 1 to get the actual value. So you multiply that by 10 negative 1, don't forget. Divide by change in extension, that is 2 minus 0.5. 2 minus 0.5. 2 minus 0.5. So this will be 1 minus 4 is 3. 3 times 10 negative 1, that will now be 0.3. Sorry. Let me just 0.3. 0.3. That's force, so that's newtons, over 2 minus 0.5, that is 1.5 centimeters, right? Because extension was in centimeters. Now we use our calculators to do the calculation and see. So that is with the help of our calculators, 0.3 divided by 1.5. you're going to get 0.2. That is 0.2. Sorry, that is 0.2 newtons per centimeter. Units is very important. 0.3 newtons per centimeter. 0.3 newtons per centimeter. 0.3 newtons. So learners, you can just follow that this calculation is not difficult. So when you get 0.3 newtons per centimeter, by that one you will have gotten what is called the spring constant of the rubber within the elastic limit. Remember, they said within the elastic limit. Very important. We proceed to the next question. What is the size of force at the elastic limit? What is the size of force at the elastic limit? What is the size of force at the elastic limit? What is the size of force at the elastic limit? So how do we handle that case, learners? Getting the size of force at the elastic limit, it's not difficult. In fact, it's still very simple. How do you get that? Remember, they are saying what is the size of force at the elastic limit. It's very simple. The size of force at the elastic limit. Let's for you to answer that question, learners, you must be knowing what is the at what point do we call that as the elastic limit. The elastic limit is the point after which the straight line now tends to bend. So this point is what's called the elastic limit, and the force that was there, maybe just use a ruler. So let's see its equivalence of force. Let me use maybe this color, maybe green. So we read the force there. So in my case, I'm seeing is 13, because after 13 newtons is when the line was not straight. So that is the size of force is 13. 13. Sorry for that. Don't know. Is the size of force is 13 times 10 power negative 1. So that is 1.3 newtons. 1.3 newtons. Question number 13. Question number 13. Say the characteristics of a brake fluid. 1. It should be incompressible. Incompressible. I don't know. Just a moment. Let me put things in order. So I've said characteristic 1, incompressible. Should be incompressible. Number 2, should not corrode the parts of the braking system. Should also, that means should be non-corrosive. Because if it is corrosive, then it will corrode some parts. Non-corrosive. Should have a high boiling point. Should have high boiling point. Should have also a low freezing point. Low freezing point. These two, someone can talk of them having a high range of temperature. High That one can be talked of as high range of temperature. High range of temperature. Why should it be incompressible such that pressure applied at one point should be equally transmitted all other parts? Non-corrosive so that it does not corrode the parts it's in contact with. Question number B. The height of a mercury barometer at a particular place is 70 centimeters. Given that the density of mercury is 13,600 kilograms per cubic meter, determine the atmospheric pressure. Determine the atmospheric pressure. So the height due to the mercury column is 70, the density is this. They want to determine the atmospheric pressure. Pressure is given by what? H rho G. As simple as that. So in the calculation we say pressure, or rather atmospheric pressure, atmospheric pressure should be given by H rho G, where H is the height of the mercury, but remember in SI units, so that will be 70 over 100 times the density, which is 13,600, times the gravity, which is 10. That gives you 95,200 newtons per square meter, or you can talk of it as pascals. Newtons per square meter or pascals, whichever you wish. The height of the water barometer at the same place. Height of water barometer at the same place. Height of the water barometer at the same place. If the place is the same, it means the atmospheric pressure is the same. Now they want the height. So still remember that atmospheric pressure is still given by H rho G, because it's the same place, meaning the atmospheric pressure is the same. So that is 95,200 should be equal to the height, which you don't know, times the density of water. We've been given 1 gram per cubic centimeter. You convert it into kilogram per cubic meter by multiplying it by 1,000. So that will become 1,000 times 10. So you learn that H is like saying 95,200 divided by 10,000. When you do that cancellation, you'll get it as 9.52 meters. 9.52 meters. As simple as that, learners. There's nothing difficult there. Give a reason why mercury is preferred as a barometric liquid. Learners, underline the word barometric. Underline the word barometric. There's a difference between this question and the one where when you will find they are comparing it with alcohol as a thermometer. So please get the main difference, barometric. So the reason is because, or rather you may be told, give a reason why water is not preferred as a barometric liquid. So get the difference. So mercury is much denser than water. Give a reason. You can simply say mercury is denser mercury is denser than water. Or you can say it has higher density. Another reason is because you can say it supports a small and measurable column. It supports a small and measurable column. Please, I'm insisting on it being barometric because many learners tend to say it's not opaque, it's what. Please, take note of that. Take note of that keenly. Calculate the minimum pressure a block of these dimensions and these mass exacts. So remember that pressure minimum is given by force over area maximum. So to get the pressure minimum, what is let's first get the force. Force is the same as weight, which is given by mass times gravity. My mass is 12 kg times the gravitational force, which is 10. So I'm getting my force, which is the same as weight, as 120 newtons. After I've gotten my force, I can now proceed and say minimum pressure is obtained by taking the force, which is 120 newtons, divided by maximum area. Maximum area can be obtained by bigger values, this and this. So 10 over 100, that is 0.1 times 0.15. This one is now in meters, squared when you do the multiplication. So when you have it like that, that becomes, so when you divide it is 8,000. That gives you 8,000 newtons per square meter. 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 Differentiate between transverse and longitudinal waves. Learners, what do we do? To distinguish between transverse and longitudinal wave, you can simply say that in transverse waves, the vibration of particles is at right angles. Maybe let me just draw a table. I can have here transverse waves. Then here I can give you to differentiate I have to use definitions. So let me just write in transverse. In transverse, the vibration of the particles, the vibration of particles is perpendicular to the wave motion. While in longitudinal, the vibration of particles, the vibration of particles is in direction of the wave motion, is in the direction parallel, let me use the term parallel, to the wave motion. By doing it like that, you will have distinguished parallel to the wave motion. The figure below shows a wave form in a string. Given the speed of the wave is this, with reference to this wave motion, determine the wavelength. What is the wavelength, learners? when you talk about the wavelength, this is the distance between two successive crests or two successive troughs. If I talk of it as this point, the crest here has a reading of 20, another crest here has a reading of 60. So the two are successive. So the difference between the two successive crests or two successive regions of troughs gives you the wavelength. So by that, having considered that, so this one here, it is 60 minus 20, so that is 40 meters. 40 meters. Amplitude. Learners, amplitude is the maximum displacement about the mean position. The maximum displacement about the mean position. So you get your amplitude is 5 meters. Remember, I've said the maximum displacement. How far is it from the mean position? That gives you the amplitude. Then the frequency. Frequency, this is the number of complete oscillations made. When you talk about frequency, there's this formula we talked of V is equals to lambda F. V is equals to lambda F, where V is the velocity of the speed, lambda is the wavelength, F is the frequency. So this means what is the speed? The speed is 10 meters per second. So 10 should be equals to lambda, which we got here as 40, times F, which we are looking for. So this will be now F is equals to 10 over 40. That is 0.25. It is frequency, its SI unit is Hertz. 0.25. 0.25. Yes, we proceed. Period. Period is the time taken to complete one oscillation. Time taken to complete one oscillation. The time taken to complete one oscillation. But also we know that period, which is denoted by T, is normally given by 1 over F, isn't it? So this is like saying 1 over 0.25. This is 1 divided by 0.25. 1 divided by 0.25. Let me use my calculator. 1 divided by 0.25. I'm getting 4. 4 seconds. Because it's period. So you should be knowing those relationships. This is waves 1. Let me see. We have a lot. So I need to up my speed. A person standing 49.5 meters from the foot of a cliff claps his hands and hears an echo 0.3 seconds later. Calculate the velocity. So you know this is sound. If I have a person here, if this is my person, then I have a cliff. This is maybe a cliff. So this person claps hand. The sound has to move this distance. Ikuja hapo igonge tena irudi. What do you learn? The total distance covered will be twice. So this person is standing 49.5 meters from the foot of the cliff. So lazima hii sound itaenda 49.5 to the cliff, then irudi by the same 49.5 ndio isikike. You know that distance is equals, just a moment, let me just erase that. Calculate the velocity. Speed, which is given by V, is normally distance over time. But now because this thing is going twice, so it is 2d over t. So velocity in this case is 2 times our distance, which is 49.5, divided by the time which it took to hear the sound, which is 0.3. With the help of our calculators again, That is 2 times 49.5, you get 99. You divide 99 by 0.3, you get 330 meters per second. 330 meters per second. What property of light is suggested by formation of shadows? What property of light is suggested by formation of shadows? That is light travels in a straight line, or rather what we call rectilinear propagation of light. So the property can be rectilinear propagation of light, or light travels in a straight line. It can also be that property. Light travels in a straight line. How true is that? You know, if I have let me just do as a demo here. If I'm having this as my source of light, then this light is going this side, then upon here it makes maybe something like a building or a block. Light was traveling in a straight line. It meets an obstacle here. This is an obstacle. It will not be able to penetrate, therefore it will result in formation of a shadow behind. So what is the essence? Light traveling in a straight line, and the property which suggests light travels in a straight line is what is called the rectilinear propagation of light. The rectilinear propagation of light. So learners, you should be able to relate such examples. Part B, a building standing 200 meters from a pinhole camera. A building standing 200 meters from a pinhole camera produces on the screen of the camera an image 2.5 centimeters and high, and a high 5 centimeters behind the pinhole. Determine the actual height of the building. Determine the actual height of the building. Determine the actual height of the building. So this is a question that relates us to have the concept of magnification. Remember, we have this relationship that height of the image over height of the object should be equal to image distance from the pinhole camera over the object distance from the pinhole camera. So they say a building standing 200 meters from a pinhole camera, this one is U, produces on the screen of the camera an image 2.5 centimeters. This is the height and high. So let me just see how that is. So what they want, the height of, determine the actual height of the building. If I make height of the object the subject of the formula, I'm going to have height of the image times the object distance from the camera divided by the image distance from the camera. Now having that, my height of the object is now going to be height of the image. What is the height of the image? Wamesema the height of the image is 2.5. So that is 2.5. That is 2.5 times the object distance from the camera. The object distance is 200 meters, converted to the same units by multiplying by 100 to bring it back to centimeters. So that becomes 20,000. Sorry, this will become like that, over the image distance 5 centimeters behind, so that is 5. When you work it out, learners, you're going to get that is 10,000. centimeters, or someone else can talk of it as 100 meters. So that's what you have to do there. You have just to relate and work it out. An object of height 2 centimeters is placed 5 centimeters in front of a convex mirror, of focal length 10 centimeters. On the grid, draw a scale. On the grid provided, draw a scale diagram to locate the position of the image. Draw a scale diagram to locate the position of the image. So they are saying an object of height 2 centimeters is placed. So first of all, let's draw our convex lens. Sorry, our convex mirror. Let's have it drawn. Let's draw. Let's draw it together. Let's have it drawn well. So if I have it like that, normally I have this as the symbol. It's convex, like that. Sorry, it's a convex mirror. So you have they are saying that an object of height 2 centimeters is placed 5 centimeters behind the mirror. 1 2 3 4 2 3 4. My god, this one will not. I've squeezed this one too much and it might not work as we expect. Wait, my god, let's see. Let's let me create some spaces. Let me create some spacing. And let me use a red pen when I'm doing the drawing, because I realized that one was not working well with me. It was not so clear for my learners to enjoy the session. Yeah, this one is very clear now. I love it. I love it how it's coming clear. So like that, it's a convex lens. So we follow the procedure that an object of height 2 centimeters. Let me draw the principal axis first. I hope you know what a principal axis is. The principal axis, it can be here. My principal axis. I'm done with my principal axis. So they say an object of height 2 centimeters is placed an object is placed 5 centimeters in front of a convex mirror. This is our convex mirror. Is placed 5 centimeters. 5 centimeters. So where will we position our object? So first of all, let me get a suitable scale to use here. Let me use a scale 1 centimeter to represent 2 centimeters. Let me use a scale of 1 centimeter to represent 2. Just a moment. 1 centimeter to represent 2 centimeters. 1 centimeter to represent 2 centimeters. And having that, the object is how many centimeters? 1 centimeter to represent 2. So this is the how are we going to put this? 2 centimeters an object of height 2 centimeters, so that will be 1 centimeter up, but 5 centimeters in front. So this is a 2 somewhere here. Let me use a ruler for higher accuracy. That is it's going to be where, somewhere there. That is 1 1. Yes, so that is 5, but now 2. Let me use a different ink. I don't know if this will be visible. Sorry. Let me just position this well so that just give me some time. Using this ruler is not a joke. I think now it's well positioned. Like that. That is now my image. That is my image. Now with our image, what happens? How do we locate our object? We've been told anything. A focal length is of 10. Very important. If the focal length is 10, so there's 10 will be 5 units. 1, 2, 3, 4, 5. Here you'll have your focal length. Then 1, 2, 3, 1, 2, 3, 4, 5. 1, 2, 3, 4. Maybe somewhere here you'll have had your C. Somewhere here. This one is still I wanted to fix this thing in one page. Let me just have it again. I don't want to give estimates. I want to give it well. I don't know why is it taking time. Sorry, apologies for that once more. But at the end, I want my learners to have exactly what I want. Let me make it here. So let me see, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 exactly. Now that one will work. One, 2, 3, 4, 5. Yeah, this one is now going to work exactly as per my needs. Sorry for that. Sorry for that. We are winding up, learners. I'm taking a lot of time in this because you can also see it's a very good paper. It's theory, but with the application of the practical part. So if you polish yourself well in this paper, even I'm sure in the practical one day you'll smile and you'll remember my sessions and invite your friends. So this one now, let me do it now quite fast. Let me do it now. That's 5 centimeters away. Like that. That's very correct. Now if that is my object 5 centimeters away and 2 centimeters high, to locate the image I have to draw a ray, or maybe let me first locate my F, because they say F is 10 centimeters. 1, 2, 3, 4, 5 here. This is the focal point. Then 1, 2, 3, 4, 5. This will be my C. That will be my C. So I have first to draw a ray parallel to the principal axis. I have to draw a ray parallel from the tip of the object parallel to the principal axis. a ray parallel to the principal axis, and this ray will appear a ray parallel to the principal axis, a ray that's F, then 1 2 3 4 5. I have F here. 1 2 3 4. F is here. A ray parallel to the principal axis, and that ray parallel to the principal axis will move in such a way that it tends to be will get diverged such that it tends to come from F. Will get diverged such that it tends to come from F, like that. Let me use a different ink. I want a higher level of accuracy here, like that. That's very nice. Then I'll also draw another ray from the tip of the object to C and to the center of curvature, and that ray normally goes undeviated. Sorry for that. That ray normally goes undeviated from the tip to through the center of curvature. This ray goes undeviated, learners. I told you this is a very good paper even to the candidates. I told you this is a very good paper even to our candidates. That ray goes undeviated. Let me just let me see which color can work better. Let me use the yellow. Let me use this one. And that ray goes undeviated, so it's a full ray in front of the mirror. When it goes behind the mirror, it will become a virtual it will become a virtual ray, like that. I'm done with that. Once we are done, so this ray went like this one, ilienda karudi, this one ilienda karudi. So where the two rays intersect, that gives you the image. Let's draw our image. So the point of intersection, I'm seeing them intersecting just almost closer. I'm seeing it getting formed somewhere closer to F. Somewhere closer to F here. Somewhere closer to F. It's virtual because it's formed behind the mirror. Like that. It's formed behind the mirror. I'm done with that. So how many centimeters? 1 2 3 4. So it is a 4 times 2, that is 8 centimeters behind the mirror. So let's answer the question. Or draw the scale. So after we've done this drawing, learners will realize the image is 4 units, but each unit was 2 centimeters. So the image is 8 centimeters behind the mirror. 8 centimeters behind the mirror. The image is 8 centimeters behind the mirror. Let me just see. Yes, like that. Just a moment. I forgot to do that. So we are done with that. State 2 applications of concave mirrors. Applications of concave mirrors. One application of concave mirrors, we have the shaving mirrors, used in shaving mirrors. Shaving mirrors. Shaving mirrors. Another application of it is by dentists to examine teeth. By dentists by dentist to examine teeth. When is an object said to be in a stable equilibrium? A body is said to be in a stable equilibrium. We say this is a body is said to be in stable equilibrium if it returns to the original position. If it returns to the original position, after slightly displaced, after being slightly displaced. Let's see the next question. Learners. That a uniform metal rod of length 80 centimeters and mass 3.2 kg is supported horizontally by two vertical spring balances, C and B. Balance C is 20 centimeters from one end, while D is 30 centimeters from the other end. Find the reading on each balance. What do we do in that situation, learners? It's very, very important to have a sketch. It's very important to have a sketch. Once you have a sketch, it will make even your own work easier. So let's first start by getting the sketch. So I'm having a metal rod with me. This is, I can say, this is my metal rod. This metal rod is being balanced, or let me say maybe somewhere. It's being balanced by some springs. I can have this spring here. I can have another spring somewhere here. So a uniform metal rod, the length of this rod is 80 and has this mass, is supported horizontally by two vertical springs. Allow I call this spring C. I call this one here spring D. Balance C is 20 centimeters from one end, meaning from here to here is 20. From here to here, that distance is 20. While D is 30, so this distance here is 30. So what is the reading? This is simple. Because it's a length at 80, at the 40 centimeter mark here, at the 40 centimeter mark here, we have its weight acting downwards. And the weight acting downwards, if the mass is 32, so weight is equals to mass times gravity, 3.2 times 10, that gives you 32 newtons. So the weight acting downwards here is 32 newtons. Find the reading on each spring balance. Let's see how we can get it. Let's assume Let's make C to be the pivot. Let's make C to be the pivot. So with this one you can say when C is the pivot, you know F1 D1 should be equals to F2 D2. F1 D1 should be equals to F2 D2. F1 D1 should be equals to F2 D2. And because now C is our pivot, if I make F1 to be this weight, so the weight is 32. 32 you multiply by the distance. Remember hapa ni 40 because weight acts at the center. So if from here to here is 20, from here to here also will be 20. So 32 times 0.2. I'm converting the 20 into meters, should be equal to my F2, which I don't know. That is the force due to spring D, times its distance from the pivot. The distance from the pivot, this is if the whole of upper is 7, upper is 30, and the whole of this was 80, meaning the total distance here is what? Is 50. So 50 is 0.5. So that gives you F2 will be now 3.2. That will be now 3.2 times 0.2 divided by 0.5. So my F2, my force at that point F2, with the help of my calculator, I'm going to get let me see, 3.2 times 0.2, I'm getting 0.64, divided by 0.5, I'm going to get 1.28 newtons. 1.28 newtons. That is the force at that point, 1.28 newtons. 1.28 newtons. Is it giving 1.28 newtons? Let me see. Because 32 times 0.2, why, if this distance, let me just crack it down. Let me see, because I'm expecting the whole of this is 80 centimeters. The weight will act at the 40 centimeter mark if C is positioned 20 centimeters. If C is positioned 20 centimeters from one end, then the pivot being at 40 will also be, if C is the pivot and I treat the weight of this metal block as force 1, so force 1 will be 32 times its distance from the pivot, which is 20. I divided by 100, that is 0.2, should be equal to F2, the force as a result of that other one. That will be oh gosh, I've seen where I wasn't doing well. Remember, let me just have this recap because I wasn't happy with that value. Let's analyze this F2. F2 is this one, but how far is it from the pivot? Already C is here. Hapa kuna distance ya 20, hapa kuna another distance ya 30, so that's 50. So if it's already 50 imeachwa huku, so the total of distance of 50 is left. From 80, the remaining distance should be 30, not 50, should be 30. This value here should be 30. Now when you multiply it by divide by 100, should be 0.3, such that now it will be now 3.2 times 0.2 over 0.3, not 0.5 as I had written. It will now be over 0.3. What do you get? Let's see from the computation. That is 3.2 times 0.2 divided by 0.3. Divided by 0.3. Let me just see. Is it making sense? Let this one be the pivot, 20 centimeters away. So E distance up and 20. This one is equal 1410. So that distance is 3. F2 F1 times 0.3. I'm getting that as just a moment, I'm having a review. So 30 times 32. Why is it coming like that? Let me just see. A uniform metal rod of length 80 centimeters and mass 32 kg and mass 3.2 kg is supported horizontally by two vertical springs balances by two vertical spring balances C and D. Balance C is 20 centimeters from one end, while D is 30 centimeters from the other end. Find the reading. I've said let my pivot be at C. If C becomes the pivot, how far F1 D1 C, the principle of for a system to be in equilibrium, clockwise moment should be equal to anti-clockwise moments. F1 D1 equals to F2 D2. I've said let my F1 be the weight. So that is 32 times its perpendicular distance from the point of support times its perpendicular distance from the point of support times its perpendicular distance from the point of support. What is that perpendicular distance from the point of support, learners? What is the perpendicular distance? That is 20. That should be 20, like that. Then should be equal to F2. Should be equal to F2. What is our F2? Our F2 is maybe if this is the pivot, our clockwise moment will be just breaking it down further. I'm just breaking this down further. Let's see. If you do it like that, should be equals to F2. How far is it? The total length is 80 already. This 120 is left, 30 is left on the other side, so that is 50. So remaining distance will be, you less 50 from 80, that is 30. 20 plus 10. Yeah, that's correct. So it will be times it should be equal to F2 times its perpendicular distance from the point of support, which is 30. Then you do your computation. Let's do the computation together. Let me get my calculator. That is 3.2 times 0.2 divided by 0.3. I'm getting, let me make it, I'm getting it as, find the reading on each balance. I'm getting it as 32 over 15 newtons. Let me also do the same, but now you know that some clockwise moment should be equal to anti-clockwise moment. Have I worked out this question well, or it is mixing me up somewhere? I'm not happy with it, the way I'm doing the sketching. I'm not happy with it. Let me have its review. Let me have its review from the start. From the start. Sorry for that, but I'm not just satisfied. So the weight here is 32 newtons. That's correct. So let me try it with making D the pivot. Let D be my pivot. If I make D to be my pivot, I know F1 D1 should give me F2 D2. So F1 is this weight, which is the weight which is 32 times D1. 32 is up and 40 equal to 30 centimeters mark from this side. This is equal to 40, so this distance here is 10. 10 divided by 100, that is 0.1, should be equals to this moment, should be equals to the other moment. Allow I call it moment C. Sorry, for C times the perpendicular distance. Sasa kama hapa ni 30, 10 plus 20, that will also be 30, right? Because this is 30 plus 10 is 40 plus 20, that is 60, plus another 20. So this is 30. 30 is 0.3. 0.3. So meaning C can be 3.2 divided by 0.3. What do you get? With the help of your calculator, you get 3.2 divided by 0.3. You're getting 10.67. 10.67 newtons. Then after I've gotten that, I know that upward forces should be equal to downward forces. So C plus D should be equal to the weight. So that is 10.67 plus D is equals to 32. So what will be my D? 32 minus 10.67. I'm getting 19.3. 19.3. I'm getting 19.3 newtons. 19.3 newtons. I'm sorry for taking that time. Seems that there's something that was not adding up, but finally it is 19.3. That is what is this subtraction? Should be 32 minus 10.67. That should be 21. 21. This should be 21, not 19. That should give you 21.33 newtons. 21.33 newtons. Question number next. The figure below shows an electric bell. Briefly describe how it works. So when a circuit is closed, the soft iron gets magnetized and attracts the soft iron armature. The hammer hits the hammer attached to that hits the gong. The contact breaks, the core loses the magnetism, and the armature returns to the original position. Therefore, the process repeats. So basically, that's what we need to put there. So we say when the circuit is closed, when circuit is closed. When the circuit is closed, the soft ion core gets magnetized. And attracts the armature. Hence striking the gong like that. The contact breaks. Once the contact breaks, the core loses magnetism. And armature returns to original normal position. The process repeats. Learners, so basically this is the process to be followed there. State the right hand grip rule for a straight conductor carrying current. When a straight conductor, it's stated like this. When a straight conductor carrying current is held with the right hand, comma, with the right hand, with the thumb, pointing the direction of current. The thumb pointing the direction of current, comma, then the fingers will point the direction of magnetic fields. Then the fingers will point to the direction of magnetic fields, State the equation of continuity. The equation of continuity is A1 V1 should be equal to A2 V2, or rather even someone, or you can even state it like this by saying A1 V1 equals to a constant. Still it's correct. The velocity of glycerin is this. In this is this. Find the velocity in this if it connects to this. So this one, you know that A1 V1 is equals to A2 V2. So the velocity of glycerin in a 5 centimeter pipe is this. So area ya 5 centimeter, we are going to get it as how do you get the area of something that is 22/7 times the if this is the diameter, so the radius will be 2.5 squared times its velocity. What is the velocity? 1 should be equal to area 2. Should be equal to area 2. What is area 2? Find the velocity in a 3 centimeter internal. So area 2, that is 22/7 times what? Times if the diameter is 3, so it will be times 1.5 squared times its velocity, which you are looking for. So you'll get the velocity there is 22/7 times 2.5 squared times 1 over 22/7 times 1.5 squared. Yes, like that. When you do that computation, I'm getting 2.77. Sorry, this one here you have to multiply it times this is centimeters, times 10 power negative 4. Also here you multiply by 10 power negative 4, so that make sure you are working with the SI units. So times 10 power negative 4 times 10 power negative 4, converting the centimeters to meters. I am going to get this squared meters, meters per second. That's the velocity. That marks the end of that paper. It has been a very involving paper. I love how it is. Thank you for your session, learners. Keep subscribing to the channel, hit the bell icon and comment so that you don't get left out. For any inquiries, learners, our hotline number is still, let me leave it at the top here. Our hotline number, in case of any inquiries and clarification, our hotline number is 0741304311. Thank you for being part of us and for making this session a success. Thank you. See you in our next session. Goodbye.